Hello, AP Physics C. Welcome to your new classroom. See the board? Um, by the way, I successfully, partially successfully, Zoomed with about 3 or 4 of you earlier, and all of a sudden you all froze and wouldn't talk back to me. And I wondered why. And then I figured out my internet went down. Something happened with the Wi-Fi. I got it working again later, but it was kind of too late. So hopefully that'll all work next time. And what we were talking about circuits. I won't completely repeat everything I said. I'll show you instead a couple of the boards that I was using. We did some circuit problems like this. Yeah, I think you can see that. There we have a 6-volt battery, a 30 ohm resistor. We calculated the current was, I think, 0.2 amperes, and we used V equals IR and P equals IV. And then we did circuits in series, resistors in series where they add up and the voltage splits across them. So the total voltage or potential difference across the two of them is the sum of the two potential differences. The total resistance is simply the sum of the resistances. And by the way, we also, we figured out that if P equals IV and V equals IR, I hope I'm holding that correctly. Yeah, I guess so. If P equals IV and V equals IR, then P equals I squared R and V squared over R and stuff like that. So we did that, and then we upped it a little bit. We did, what did we do? I erased it and used it for one of these. But we actually did a circuit where we had, something in series with a couple of things in parallel. Your book is pretty good about explaining this. The stuff is not really hard, but it does take, there are mistakes that can be made. Let me point out a couple of things. One is that anytime you have two resistors in parallel with each other, the potential difference across each one is the same because it's an option. It's like if you took the elevator up, let's say 6 floors, and you went 2 floors down here, you got 4 floors to go, whether you go through this one or that one. There's that additive, thing about the voltages all the way around. Sorry to have to add up. In fact, it's kind of like the loop rule I'm going to talk about in a minute. When you work a problem that has both parallel and series things in it, you sort of think about it like parentheses, the do me first part. I think it's fairly obvious here that you would find the equivalent resistance of the two in parallel with each other and then add that in series to this one. Or if you had two resistors in one of the branches of the parallel thing, you'd use the series rule first. I think it's obvious. And then parallel that with this. It's sometimes a good habit. I'm not going to make you do it necessarily, but you can draw a series of successively simplified circuits where you start with, this, and then you crunch it down to just this, and then you crunch that down to this, and then ultimately it's like one big resistor. If you have any questions on working problems like that, I'm going to be on Zoom. I'll post all the stuff on PowerSchool about what time. I'll be on Zoom so that we can get that straightened out. What I want to talk about now, though, is Kirchhoff's rules. I briefly introduced them in my sort of first attempt at a video yesterday, but let me do it again real quick. Kirchhoff's rules are super simple. They're kind of obvious, but they still deserve to be said. And it's strange how the simplest things sometimes can end up producing complex. Sometimes you can get in kind of deep with them. But in any case, the rules are like this. If you have a circuit and say here's the battery and, there's like a resistor here and a branch here, something here. Define a term, EMF, electromotive force. I don't like the name because it's not a force. It's an energy per unit charge. But it's conceptually like a force because it's kind of like babushka trying to push you through, It's kind of like the voltage of the battery. But it's not necessarily the potential difference across the terminals of the battery. It's kind of like the inherent ability of the battery to make the current flow. If you think of the height of a water tower being sort of the thing that gives it the ability that head of water, that vertical distance there, to make the water flow out. You can think of the battery like a pump, maybe. It's like a pump that's trying to force current to flow through resistors. So it's metaphorically a force, but it's measured in volts. I'll go ahead and clarify the difference between EMF and a voltage across the battery. Go ahead and do that. For example, what if we had a 12-volt battery and you had it hooked up to a resistor inside, it's a 60 ohm resistor? You could quickly figure out the current's supposed to be 0.2 amperes. Nice, okay. But it turns out, and by the way, if you put a voltmeter, I did bring up a dinky little voltmeter. I won't get it up right now, but if you check the voltage across the battery, ideally it'd be 12 volts. However, the guts of batteries, all that chemical, whatever stuff's in there, whatever kind of battery it is, has resistance. Inside the battery is what you'd call internal, accidental, unavoidable, wish you didn't have it, be nice if you didn't, resistance. So what happens is, if I were to have, say, I'll make up a number. I don't know what number I want to make up. But let's make it terrible. Let's say this is an awful battery, and it has 40 ohms of internal resistance. It's not something you put on it. It's just in there. Now you see the total resistance, including the load out here, is 100 ohms. And 100 ohms is going to reduce the current down from 0.2 to 0.12. And if you measure the voltage across the battery with some meter, a voltmeter, I'll try to show you voltmeters later, we'll do that one day. If you measure the voltage across the battery from here to here, because that's inside the battery, you're going to get this 12 volt rise here, but you also have a drop of 0.12 times 40, which is 4.8 volts drop across this. And your voltmeter would say 7.2 volts. And you'd probably say, I got a bad battery. Well, I've actually done this with car batteries. This has actually been an issue sometimes. I remember multiple times I couldn't start my car. I didn't know if it was the battery or the starter, what it was. So I would put a voltmeter across the battery. It's supposed to be 12 volts, and it'd be close to it. But when you try to start it, the voltage drops because current tries to flow. And if there's a big internal resistance, that's not the only thing that can go wrong with the battery, I think, but if it's got a big internal resistance, the voltage will plummet as you start to use it. Now, the EMF of the battery is still 12 volts, but the terminal voltage across it is less because some of it's getting eaten up, so to speak, with internal resistance. I guess maybe I've made my point with that for the moment. I said I was going to talk about Kirchhoff's rules. Let me do that. So, Kirchhoff's rules, super simple. One of them is called the junction rule. The junction rule is just saying that, like, what goes in must come out. I might say I1 equals I2 plus I3. Now, that requires context. I need context. Let's say this is I1, and this is I2, and this is I3. And there's a junction. The junction is where things run together. It's, intersection. The traffic flowing in has to flow out. So, of course, what comes in must go out. I1 must equal I2 plus I3. That's just kind of obvious. This is something you could state at any junction in a circuit. If I had more branches, I could say it there too. Then there's the loop rule. I talked about this yesterday where I was talking about the running courses, loop courses with people who did not understand that however much you go up, that's how much you go down. I can understand having a preference, but don't tell me that you go uphill more this way and downhill more the other way. No, you do the same amounts. The loop rule says if I add up the voltages, the potential difference changes along any closed loop in a circuit, the answer is 0. And it goes like this. If this is a battery E1, EMF 1, that's how many volts it tries to make. You go like up E1, down, let's call this R1, R2, R3. You go down I1, R1. Let's take this trip. That's the way we choose to run the course today. Let's go this way. Then you go down, because when you go with the flow through a resistor, you're dropping in potential, because that drop of potential makes it go that way. So, I mean, you could run the course the wrong direction, then you'd have to say plus. Just reverse all the signs. Down I2, R2. And you know what? Back to the lobby, back to the elevator, equals 0. And likewise, you could take the other route. You could go up E1, go down I1, R1, because you had to do that. But then you could change your mind and say, let's run this course today. Let's do that. Down I3, R3 equals 0. And you end up with a system. Oh, by the way, one more loop you could do. You could do this loop. I'll briefly say that's not mathematically linearly independent of the other two. It's like the difference between the other two or something, or their sum or whatever. You might know that, like in math, you might have redundant equations over specified, so well, kind of like that. You don't need to do that loop because it's like the sum or difference of the other two. So this is enough. Hey, you know what? It's 3 equations. You know what? There's 3 unknowns. The 3 currents are probably the unknowns. Let's say they are. Let's say the resistances are known. So I could solve that. But why? I know how to do this anyway. It's easy. I just take these 2 here, say they're in parallel, do the little 1 over rule to get the parallel, the effective resistance of that. Then I add in that one because it's in series with them. And that's like some big black box, big mushed together resistor out here. It helps me find I1. Once I know I1, I'll find the voltage drop from V equals IR across this. And with that part of the voltage drop accounted for, I would know the voltage drop across here and quickly find these currents. There's multiple ways to do it. Why? Why bother? You wouldn't have to. Pointless. Nah, but wait. I could really mess things up by putting another battery here that I'll call E2. Now, I might put it in this direction. By the way, whenever you draw the longer line is the positive, the shorter line is the negative terminal. This is acting like a pump, attempting to drive this current in the other direction. It could if it's a strong enough pump. If this is a really strong battery, big, strong babushka, lots of volts, it could cause this current to flow the other way. Now, probably what would happen is it would flow the other way and come up here and join in with this and just make a whole heck of a lot of current through this one. But it's conceivable it could be such a strong battery, it might even drive current backwards through that one, I guess. I'm not really sure. It's actually sort of fun if we had class time. If we had like a 75-minute period, we could play with numbers in this and have people guess numbers and use your intuition. I kind of like that. I'll have to get a little more to the point here. But whether or not it reverses the current or how it affects the currents, it's at least going to reduce this current and increase this one and probably reduce that one intuitively. Just thinking of pumps and water, I'm thinking that's about what happens. But exactly what happens? Well, I got to modify my little equation out here. Let's see. This one where I went through I2 is unchanged. This one down here, though, is different. I've got one more little piece here where it goes like down E2 equals 0. Now, in a typical problem, there would be numbers. There would be values of the resistances and the E's, and maybe you're finding the currents. Of course, it's possible to specify other things. Usually they're set up like the batteries are given, the resistors given, trying to predict the currents. And it's nice to do labs like that. Maybe we'll, maybe we won't. But anyway, so you have a system of equations. It'll have numbers in here instead of just all letters. How do you solve it? You're good math students. You know ways. What ways do I know? Substitution. That's the old standby first thing I ever learned. I'm prone to try to substitute I2 plus I3 for I1 anywhere I see it. Then I get multiple I2s. I don't have any I1s anymore. And then it's still kind of a mess. And then maybe I substitute out of here into that. Some people are more skilled at that than others. You know, it can be done. You can get answers that way. Then there's fancy things. There's this Gaussian elimination thing that I vaguely remember learning way back when, some algebra course. You can do Gaussian elimination. Then there's fancy stuff like matrices. You can set this thing up as a matrix, and I guess you invert a matrix and multiply. You know, it's one of those things. I think I know how to do it. I'm going to do it right now. But I know what a lot of people know how to do. They know how to stick it in their calculator. You got some kind of solving thing in your calculator. It's one of the fancy HPs. You probably have this thing that'll solve a system of equations, even bigger than that, even more than 3, and spit out your answers for all the variables. Regardless of what approach you use, you should understand the rules. Incidentally, there's the question of, so what do you do, say, on an AP test? Do they give you these things on there? I'll tell you that I rarely see straight up like free response Kirchhoff's rules things. Instead, I think they might slip it in with multiple choice type things, where, you kind of need to know and apply the loop rule and or the junction rule in a more limited context where you don't spend like 15 minutes trying to solve a system of equations. It's a good exercise to do, but under test pressure, maybe they don't do that quite as much. More quick ways to get to it. Got to say something though. I taught this for probably 27 years or something, knowing all the different ways to solve the system of simultaneous equations. And one year, about 6 years ago, I'm guessing, something like that, I had sort of an obnoxious student. I mean, he's a nice guy, but he just was like, for instance, there was a student who left the school, and every day when I'd ask, anybody absent today, this guy would always say that guy's absent. He'd been absent. It's like the 150th time he'd been absent. Still had to say it. So it was a little annoying. So when he suddenly blurted out a suggestion for how to solve this, my initial reaction was skepticism. He basically said, why don't you just, and said something I'd never heard of before. And I said, nah, I don't think that'll work, especially coming from him. You know what? He showed that it worked in that example, and then every example we came up with, it worked. I wish so much you were here to, good grief, my dog is barking. What are y'all barking at? Oh, well. Back to work. I wish you were here to try suggesting things. Moment of silence while you try to think of what the very clever thing he said to do was. That's enough moment of silence on video. He said, why don't you just solve the problem with only this battery, or say only this battery in it. In other words, figure out the currents when there's only this battery, and that was just not there. And then separately solve the problem when there's only this battery and not that one. Then just add the answers up. It sounded too easy. It works. I think I've heard of it being done. My son was taking major mechanical engineering at Southern Poly, Kennesaw, and he had a professor who did that. Oh, there's people outside. I'll finish up here in a minute. Anyway, so Kirchhoff's rules, however you want to solve the system of equations, you can get the currents. Now, I do want to talk about a little bit of other stuff. Let me see. Here's a quick one. Sort of quick. Quick to at least mention it. Remember I said the thing about the internal resistance? Here's a question. What if you got a certain battery here, E, let's call it E, only one of them, and you have a little R that's the internal resistance of the battery and big R out here. And you want to make the brightest light bulb ever. That's your light bulb. Brightness is power. The more joules per second, watts the thing gives off. It heats up, gives off that. So you want a big P. Now P is equal to IV. It's also equal to I squared R. it's also equal to V squared over R. And the question is, what kind of an R makes a better light bulb? Is it better to have a big R or a small R? Well, according to P equals, let's see, which one do we want to look at? I is not necessarily known, so maybe we know, well, we're controlling R, we know V is this. So forget about the internal resistance, forget about that little R there for a minute. You know what? This is the same as E in this case. I would just make that as, I'll just make R as small as possible. Good grief, all you gotta do is have a really, 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 really small resistance, and then you get a super duper power, and you can make like an infinitely bright light bulb with a zero resistance like resistor, like a superconductor. Doesn't work that way. For one thing, where's the energy going to come from? You know, you can't have an infinitely bright thing with a finite battery. Something's wrong. One of the things that's wrong is that the battery has some internal resistance. Now, it is true that the smaller you make this resistance, the more current flows. It's still going to flow. Hold on a second. It's my wife. You get the interruption. I'm back. So anyway, we want to maximize this brightness over here, but you know that you're not going to have infinite current flow because this is going to eat it up. So what you really end up with is the problem that the power you're going to get is equal to, see how I want to say it. I'm going to say I squared R. I think it's what I say. So I is going to be E over R plus R, and that's times R. This is going to be the current, and this is going to be the resistance. Oh, but this is going to be squared. Square it. So you end up with power equals E squared over parentheses R plus R parentheses squared times R. And I want to maximize that. To maximize it, I guess we might want to take the derivative of it with respect to the variable, which is big R is what we're playing with. So you can take the derivative of this with respect to big R and set that equal to 0 and solve. If this were class time and I had plenty of time to do it, I'd have you sit there and do it. If you're really curious, self-motivated, you can pause the video before I tell the answer. Pause the video, see if you can find what condition yields the maximum power. Here's a brief pause for you to pause. Pause. And we're back, and maybe you figured it out by now. And I'm going to give it away because that's what we do in virtual, remote school. The answer is R equals R. So basically, you can see that a battery with a smaller internal resistance allows you to maximize the power with a smaller load, and then you can get a brighter light bulb, I guess, out of that. But it certainly puts a limit on how bright your light bulb can get because the battery's going to start eating up too much of the power anyway. Now, so we've covered that. We've talked about the, something else I got to mention. I want to briefly mention because this is worth one or two multiple choice questions on the AP exam. Here's a quick thing. We've got the whole idea of where a resistor gets its resistance. This is actually in the beginning of the chapter. So basically a resistor is like some kind of a gauntlet that something has to run. Your current's trying to go through this thing. It's getting slowed down by it. It's kind of having to work its way through the crowd. And you might ask yourself, what properties of the resistor are going to make it be real resistive? One thing is if it's long. The longer it is, the more trouble it is to get through. So I certainly think that, resistance should be proportional to the length of the resistor. I would think so. It also is related to the cross-sectional area. Now, by the way, This is easy to understand once you've done the resistors in series thing. If I were to chop this resistor into two parts, like R1 and R2, then it's pretty obvious that R effective would be R1 plus R2, so that, if these were equal, for example, then the total resistance is twice. Of course it is. What about the cross-sectional area? Here's the cross-sectional area of the thing. What if you imagine splitting the area in two? And then you could talk about maybe this like a semicircular cross-section, half-cylindery thing that's got an area, a small area, whatever it is, and it's got a resistance R1 and the other one's R2. Can you see that those two things are in parallel? That means that the total resistance, in fact, would be half of either of them alone. This is like opening up an extra lane in Wayfield Foods up there and allowing more traffic to flow by having twice as much space to get through, twice as much area to pass through. So, of course, that makes a lower resistance. And, of course, it's half, according to the little rule, the 1/over rule, that would show that. So, R should be inversely proportional to the area. So, R is proportional to the length over the area. But it's a proportionality. Something else matters. And of course, what matters is what the heck is it even made of? If it's made of wood, it has a terribly different resistance than it's made of copper, or gold, or zinc, or air, or water. All these different things have different amounts of resistance for a given configuration, shape, and length, and all that here. So actually, there's this thing called resistivity. And the resistance is equal to the resistivity times the length over the area. And you can play all kind of games with this. Like, for instance, imagine having a certain amount of metal and you extrude it out to where it's, say, twice as long and half the area, same volume. The resistance is going to go up by a factor of 4 because it's twice as long, but it's also only half as big around, or big, not around, but area. So that would make 4 times the resistance. They like to ask questions like that in the AP test. There's probably another thing or two in this chapter that we need to look at. You need to be working on the problems. I would like to use our Zoom time for questions about those problems if you have them, for any clarifications. About 3 or 4 of you zoomed in today. Next time, I'll post this shortly, maybe more people can. I hope you managed to listen to all that, even if it wasn't all at once. And we will talk very soon. Bye.